Good morning, everyone, and welcome to session number 5. I have to tell you that Suzanne has set the exam date for the 19th of March. So we're working towards that. So I hope you are not only following these tutorials, but that you are reading and reviewing some of the lectures as we present them on YouTube. So over to you, Mike. Have a good morning, everyone.
Thanks, Ignatius. Well, hello, everybody. Let me get my camera on here. It's I just had my coffee, so I'm feeling pretty good this morning. Shannon, just to answer your question on the frozen water pipes here. We bury our pipes very deep. We don't have frozen issues, but sometimes we do. And depends on the type of pipe you have. A lot of our pipe is metal type, cast iron or ductile iron pipe. And it usually does pretty good, but like old and the water expands inside, it does destroy the integrity of the pipe, which is why we bury them so deep. We don't have a lot of issues with frozen pipes, even though the temperature is very cold, because we bury them very deeply. And at least, 6 feet is pretty normal for water pipe and sewer pipe to be buried here in Canada. And you can imagine the repair is and what happened in Texas, water pipes are very shallow, 1 or 2 feet below the surface. So when it does freeze, that's where you see a lot of damage. So the plastic pipes, even copper and any sort of metal type pipes, they will just split right open and cause a ton of damage. So. Okay, welcome to week 5, and a fairly busy day today that we're going to have. What I've done is I've put together intakes, coagulation, flocculation, and sedimentation. Huge day when it comes to learning and the big start of the water treatment process. So pay attention today. There's going to be a lot of little concepts that we're going to learn about all these topics. So let me just get the presentation going. At any time, if it's such a small group, which is great, I'll be monitoring also the chat function so I can kind of see what's going on. And let me get the presentation started for you. All right, can you guys see the presentation? If you can give me a thumbs up, please, if you can, just so I know that you guys can see it. Perfect, awesome. Dwayne, you don't have to have your camera on if you don't need it, but it's nice to see somebody. All right, so this is the intakes, coagulation, flocculation. So let's get right in. Okay, for just a reminder, my name is Mike. I've been doing this for close to 25 years in the industry, as well as in both as an operator and in the management setting. Been teaching now, oh man, since 2005. I've been teaching, especially specialty climates such as, which we talked about a little earlier. I like a challenge when we teach. So we're going to split this up a little. We'll start with some intakes and screening, and that's always the first step in the water treatment process. And it doesn't matter if we're going to be surface water source, which we talked about, or the groundwater sources, because surface water, again, you're going to have a screen. We'll take a look at one in a second, but a well casing, and when we put our wells into the ground, there's usually a screen on that, and that's going to keep out not the twigs and the fish like the surface water, but what it's going to do is keep out the sand. So there's little mesh screens that are put into the well pump. So this is not just a surface water thing, but it's both surface water and groundwater. We're going to talk about a little bit about the types of intake structures, where we're going to put these, how does it fit in with our treatment process. First treatment or first barrier, which we call in a multi-barrier process, is to remove all large objects from the water stream. And again, we talked about what those could be. Fish is a big one, little sticks and the little bits that can get into the treatment process. We don't really want them here. So we need something, a screen. What you see here in this picture is a typical screen that you're going to see. Usually, you know, it's very meshy here, and if you look really closely, you can see these holes right here. So the fine screen keeps out all the, you know, the really fine material. We don't want this in our treatment facilities because then we have to deal with it afterwards. I'd rather get it out right away. And that's a typical screen. Sometimes these called Johnson screens, and that's sometimes typically what they could be called. Again, there's a bunch of different. For surface water, you can have a submerged intake, which is really typical. It will sit on the bottom, very similar to the one we just saw here. It'll be anchored somehow. There's two types. You can have a single level intake. So a lake that's really deep will have maybe a single, but sometimes there's multi-level. And we talked about the turnover in the lakes, how sometimes temperature can make the lake turn over. And sometimes the water quality can change throughout the different levels in the lake. And some places have a multi-level intake to allow the operator to change where in that lake that the water's coming from. We talked about the groundwater one, right? And that's basically, instead of an intake, they'll call this a well screen. And it does the exact same thing. Here we're keeping out fish, twigs, and for groundwater, we're keeping out the sand and the small sand particles. You got to look at the design of your screen. Now, screens could be used, you know, if your water's really clean, clear, it might not be have to be as fine. Because remember, the more fine your screen is, the more it could plug up. So you always have to remember that. A lot of the big stuff here in surface water, again, apart from the little twigs and fish, is algae. And we want to keep algae out of our treatment facilities too, because that really does make a mess as well. Basic types that you'll see on the test is a bar screen, and that's almost like a sheet of, and water has to kind of go through a filter or a mesh. The wire mesh screens are a little bit more, they got bigger openings on there. It looks like a big piece of mesh. And the micro strainers are going to be very similar to that picture that we saw earlier. They're more like this. And sometimes they are self-cleaning and they'll rotate so they'll clean off. But most times they're not. We have a big giant one like that. And once a year, I actually hire a diver to go down and inspect and clean those intakes to make sure that they're doing their job. Again, they're made out of metal, right? Or some sort of stainless steel usually, and they should be inspected and looked at just in case. Some of the bigger ones for huge facilities or facilities that have really polluted water water will get pumped to some sort of traveling screen or some sort of automatically cleaning bar screen. And what that will do is actually make sure that big water contaminants are removed, and that when that screen's running, you're always cleaning those screens, very similar to the process. So now that we've cleaned the big stuff out, right, that's the easy part. Let's, from our water source, whether it's surface or ground, we've got the big things out of there, and that's going to be a big help. But now let's talk about some of the smaller things. And some of the things we're going to talk about now is coagulation and flocculation. One thing about these two things is that these little tiny particles are the hardest particles to get out of water. And so we're going to talk a little bit about these particles, and we're also going to talk about how do we get rid of these particles. These particles are natural, right? They come in different concentrations, sizes, colors, everything. It all depends on where your water comes from. Again, if you have lots of clays or silt or different vegetation, that's going to change the type of water coming in. For us, surface water, again, because it's open to atmosphere, right? We talked about the runoff and all those things that can get washed into a water course. It's not just dirt. Dirt's pretty easy to get rid of when we deal with water treatment. But what we have to do is look at some of these harder to remove particles. And that's really what we're going to look at today. Two of the biggest things that we need to deal with is something called colors and organics. And if you want to think about that, colors and organics are very closely linked, which means that if I have more color, I have more organics. One of the biggest things to talk about here, though, and this we're going to keep talking about, is everything comes to organics and color has a negative charge. And we've all played with magnets when we were kids. So negative charge is real. It's no different than that. Negative charge. What's in there is sometimes you get this humic and fulvic acids, right? If we've all had a cup of tea, right, we've basically put leaves into water. And these leaves will impart a color into the water and a taste. And that's really what's happening in nature as well. What you're getting here is these humic and fulvic acids are substances that are washing into the water. For us, when we make tea, that's a pretty tasty thing. But when it comes to putting this in our water, that sometimes can be a problem because our customer doesn't want water that looks like tea. We'll talk about color again in when we do water quality in a couple of chapters from now. And there's two types I want you to be aware of. And one's called true color and one's called apparent color. And the difference between the two is that one is filtered and one is not. And so when I do my water testing, I will have color. And that's what I want. It's the color that the water, that the particulates dissolved in, without the stuff floating around in there, because the stuff that's floating around in there can also cause a color. So apparent color is both dissolved and sustained color. What we're really concerned about is the color that is dissolved, and that's what we're going to be dealing with here. Really important concept here is the smallest particle, which is the one that's 1 micron, and that's pretty small, like human hair. It's called a colloid or colloidal, and that's super important to think about. Those are tiny, tiny, tiny little particles. They're always negatively charged, and like we talked about, the negative charged color and organics, they're always in the state of repelling each other. Think of the magnets, right? So when I'm dealing with these magnets down here, repulsion. If I had a glass of water, so even in my coffee cup right here, if I had a water in there and it had lots of these colloids in it, which is color and organics, that's the stuff we see in our water, and every tiny, tiny little piece of color and organic has a negative charge. What are they doing in there? They're repelling. And because they're repelling, they stay in suspension. They don't come out of solution. So they just bounce off each other and they stay in suspension. Try this at home. Make a cup of tea. Leave it on your counter. In a couple of days, it still looks like tea. It has not separated. And that's because it doesn't stop. It's always moving. The particles are always repelling each other. And so inside, under a microscope, all these little particles are repelling each other because they're all negatively charged. And that's a problem. So how are you going to settle this stuff and get it out of solution when they don't stop moving? We'll talk a little bit about color again. So again, sometimes what we see is the words NOM, and right here. So color tends to be associated with the presence of NO, and that's basically what it's natural organic matter. And this could be from usually vegetation. When it decays, it gives off little particles. There's humic acids are humic substances, and we talked about, similar to how we made tea earlier, right? It's all these acids that impart into the water. They have that yellow or that brown or that rusty color to the water. And again, it's compared when we check it in the lab for color. And that color we looked at through the absorbance of 230 nanometers, or a UV254. And these are devices that measure color. And again, when I have color in my water, it equals organics. So more color, more organics. We need to remove this color. So UV254, and that's usually, we saw this a little bit when we talked about disinfection, right? There's a wavelength when we deal with getting rid of the bacteria with UV. That wavelength can also be used to check for color or measure for color. It's correlated to the absorbance of the UV radiation at 254 nanometers. And so some devices are actually called a UV254. And again, it tells me how much organics are coming into my plant. This is a fairly new technology. We started using that. My plant, I have 2 of them. So I measured the amount of organics coming into the facility. So now I can set my treatment process. But it also, too, I check it on the way out. So I make sure how much organic removal or color removal did I do. And I can measure it using this UV254. I'm also testing for color in the lab. So I'm looking at color coming in and color leaving. So those are 2 checks that I do. So how do we get rid of the color? It's removed through the coagulation process. So let's talk about that next. Now we talked about these colloids, which are color and organics, right? And now let's get rid of this stuff. The note before we go on is that those disinfection byproducts that we talked about in the disinfection chapter of the course, really color and organics mixed with chlorine causes these disinfection byproducts. And remember, those are methanes or those haloacetic acids. So the more color and organics that we don't remove before we chlorinate, this can cause disinfection byproducts. So it's really important, this coagulation process, we get this right. Because if we can get rid of these things now, they don't cause byproducts for our customers later on down the line. Turbidity is a big one, right? And remember, turbidity is not dirt. It's not what we thought. Because I know when I first started, turbidity was dirt. It's dirty water. It's not. It's cloudy. And this cloudiness here that causes this color in this picture is from those little colloids. So in this test tube here, this vial, what you'll see under a microscope is all these little particles repelling each other. They might be little vegetation or plant life and bacteria and all these things, and they're all negatively charged. They're all moving around in there, and they're not going to settle for you. They're going to stay in because of that. So if I put this through a filter, it really probably won't remove a lot of it. And so our job is to get this into a form where the filters can catch it, or I can remove it through another way. And that's what we're going to talk about next. Because the whole water treatment game, and you'll learn that in a bit, is that there's lots of stuff in water. And our job is to make it appear so that we can remove it. And that's the easiest way to think about water treatment. Again, we go back to these charges. Charge chemistry is huge, and especially in surface water treatment. We know colloids remain in suspension in the raw water because they're mostly negatively charged. And again, much like magnets, these particles will repel each other and therefore stay in suspension. So you think, wow, we got to get these things out of here. How? We add something positive. So think about coagulant. It's nothing more than negative or positive charge, so liquid positive charge. That's what we need. We need to, chemistry anyway, destabilize. Right? A fancy way of saying add some positive charge. We know that positive and negatives will stick together. And when they stick together, they stop moving. And that's perfect. That's exactly what we want here. We want to get these out of solution or get them to stick together, because now when they get bigger, I can remove them through a number of different ways here, which is perfect. When I do pull this stuff together and it creates these little tiny flocks, and that's what they call these things. When I start pulling these things together and make these fluffy little clouds, it's called flock. That's what we want, because that's flock is going to get caught in our filters or get removed in some of the processes here that we'll talk about in a little bit. And that is charge chemistry. So what is coagulation? So we want to disperse a coagulant. Remember, that is positive charge or liquid positive charge. It destabilizes our magnets, right? Positive to negative, the particles, and forms a precipitate. We talked about precipitate is that flock. We have to mix it through something called a rapid mix or a flash mix. And that it has to be super quick to make the reaction work. We want that as quick as possible. We want that an effective mix of positive and negative together in order to make the reaction work. It shouldn't just be a really, you pour it into some moving water. It needs to be agitated and really mixed to make this work. If you don't, you're not going to get effective coagulation. So it's really important to have rapid mix or a quick flash mix. And that's the terms you'll see on the test. The whole purpose of coagulation, again, is to reduce both turbidity and water. It results in safer water, which means we get rid of these colors and organics, because they're not going to make you sick. But if I add chlorine to it, it could create byproducts. It also creates water that doesn't look really good coming out of your customer's tap, because it's going to be yellow, right? It'll be cloudy looking. And those are things that reduce public confidence in your water. So you want to make sure that when we're doing this, we're getting rid of that cloudiness or that turbidity, and we're getting rid of those colors, which could cause taste and odor issues later on. One of the words here we should talk about is cationic. And that is a really fancy way of saying positive charge, right? So through the addition of positively charged coagulant, and they'll call it cationic, we're going to destabilize, right, the magnets together, and we're going to attract all these together. So instead of having all these negative particles bouncing around in there, we're going to start getting these snowballs of, they look like snowflakes almost, of product, right? It's all these little colloids are going to be sticking together with the coagulant and in creating a flock or something that's heavy that I can remove. This word cationic means positive, and we can also buy anionic, and that's a negatively charged coagulant. So sometimes that's used as well, depending on the type of product. Understanding if you're getting rid of color and organics, which most of us will be in our treatment processes, that is what's needed. Some of the main chemicals that are used for these coagulants or these liquid positive charge is, when we look at the periodic table, there's two metals on there that exhibit high positive charge. And one of them is going to be aluminum, and the other one's going to be iron. Now, funny enough that in the water industry, especially in Canada, that we use aluminum for water and we use iron for wastewater. Now, in Europe, it's the complete opposite. So I'm not sure what type of coagulant, if any, that you guys use there. But the main one here is aluminum based, and it's called alum. When you look at the ABC test, the test that you'll be taking, they will be looking at alum, or an aluminum based product, to the most popular or the most widely used type of coagulant. It has an Al+2 charge, a big charge, but so does iron. Iron does have a great big charge as well. These are some different types. There's aluminum sulphate, also called alum, polyaluminum chloride, which again is a different of this. Those are two widely used aluminum ones. There's ferric chloride and ferric sulfate, and those are very popular iron-based. So there's a question there about the standard length of a pipe in which coagulation has to take place. It is, and a lot of the time, and we'll talk a little bit about the mixing, but when no real standard to it, it depends on how you're going to mix it. Some places use water pressure, so if the water's moving one way, the coagulant will move the other way, and they'll mix like this. There's other ones that use a mixer. Those are really, or what they'll do is they'll inject it to the base or the inlet side of a pump, and they let the pump impeller do the mixing. So some of the smaller systems, that's how they do it. They'll inject the coagulant to the base of the pump or the inlet side of the pump, right? Or they'll go through a static mixer. They'll have a mixer that's inside the pipe. It just allows the water to go through and mix. So depending on the size of your system, there's different ways to rapid mix this. How effective you are in doing this depends on a couple of these factors. And again, we got to make sure that we're not underdosing or overdosing the chemicals. And again, there's some things that we can do to make sure that we're doing the best job we can. Again, some of the tricks for the test. Alum's the most commonly used. Alkalinity, and we'll talk about alkalinity, is the factor. The pH is best between 5 and 7. As you start getting past 7, it doesn't work as well, or some of these coagulants don't work as effective. They still work well, just not as well as they were. So they like that 5 to 7. And sometimes if you can't be in that range, if you're too low, you're going to have to do some pH boosters and get some pH adjusters, like a lime, to make it a bit better, or you're going to have to reduce the pH a little bit. And you can use CO2 or some sort of acid to do that. We'll get into mixing, and we started talking a little bit about mixing. Coagulation is accomplished by mixing a suitable chemical, and we know today are cationic coagulant, and it's probably going to be alum or some sort of derivative of alum. A violent and rapid mix is required, and then we're going to follow that by a longer, gentle mix. And we'll talk a little bit about that. One of the ways, and I've seen this, like I said, large propellers can do it in some of their big systems, and that's in my plant. That's how I kind of do it. I add the chemicals. I have a fairly large mixer in there. Some of them are, like I said, we inject it to the base of a pump, or we put it, against the flow. Now, Shannon, you had a question about would chlorine gas be a good pH reducer? It can be, but we got to be careful, because if we're going to add it before our process, it has a lot of organics in it. So if you're adding a little bit too much chlorine, you could create those byproducts before you even remove them. So it does, though. Chlorine gas does reduce pH, but I would rather use an acid or something that would create a byproduct first. And so we always got to be careful about using a chlorine gas up front. One of the big things, the mixing process must be in uniform, and that's the biggest thing. We want to make sure all that water in there is mixed, and it's mixed properly, and it's mixed in a way that it's always being consistent. Because if I'm only mixing some of my water and maybe we're overdosing some of it and underdosing other parts of it, that's not going to make for a good treatment process, and you're going to run into some trouble there. So what happens? What happens from when we do add this cationic coagulant? The aluminum portion, right, which we talked about, which is part of it, it's going to react with the alkalinity in the water. This is the most important part. This is the biggest mistake operators make. I'll draw a little picture here. And you're going to see this. So, excuse my poor drawing skills, but this is an aluminum molecule right here, right? So what we have is we're going to have a bunch of arms here. And I know this looks horrible. Each of these arms here, there's a sulphate. And there's going to be 6 sulfates. And this is alum. When I take it out of the package, this is, if I look under a microscope, this is what it's going to look like. It's aluminum in the center, and there's all these sulfates around the outside, aluminum sulfate. And I'll move. What's going to happen when I add this to water, there's an exchange that happens. In the water, I'm going to have a bunch of OH minuses. And those are called hydroxyls, or they're also called alkalinity. What's going to happen that all these sulfates are going to go into the water, and all the OHs are going to go onto each arm. So basically 6 OHs are going to bond with this, and all of these blue guys are going to go into the water, all these SO4s. So we're going to put more sulfide into the water, and all the alkalinity is going to attach to these arms. Now, here's the problem. If I don't have enough of these OHs to fill the arms, all 6 of those arms have to be full in order for this aluminum to work. So, alkalinity is super important. And here's the other issue that happens is that water with the most color, usually creek or some sort of surface water like that, have low alkalinity, which means that, I have a big mistake operators make is I have colored water, and it's really colorful. I add coagulant, it's not getting all the color out. What do? You pour more coagulant in, and it's still not working. Chances are you ran out of alkalinity. It's like buying a car. Great, fancy, brand new, fancy sports car, but it has no gas in it. and it's not going to go anywhere. So think of alkalinity is the gas that makes the car go here. And if we don't have enough gas, you can have the nicest car in the world, but if you have no gas, it isn't going to work. Same idea here. So we have to make sure in order for this aluminum portion to work, all 6 of those arms have to be full. In essence, you can see all these little charges, and again, all these negative charge particles floating around in there. We add this positive charge. You can see how once we added that positive charge, they clump together, they create these bigger flocks, and this is great because they'll do one or two things. They'll float around in here sort of, so I can easily remove them, or they'll settle to the bottom. And now I can remove them through a different way, and that's what we'll talk about next, which is fantastic. Let's talk a little bit about the coagulant dose. So we're going to make sure that we're not overdosing or underdosing. And this depends on the turbidity and color of the water. And again, once you set your dose, you have to monitor that, because if you're taking from surface water, it might change a lot out there. A rainstorm, for example, could wash more organics into your water source. So when I have more color and turbidity coming to my facility, I'm going to have to put more coagulant into that water. Temperatures also make a big difference. Once that range between 2 degrees and 20 degrees are going to increase the reaction. Cold water, like water that's 1 or 2 degrees, that's what I'm dealing with today. Water that's 1 or 2 degrees always takes a bit more coagulant to treat. Whereas water that is over 20, hotter water or more room temperature water, also increase the chlorine demand or the coagulant demand. Slower reaction when it's cold, or sometimes the reaction is actually too fast and it doesn't work. Again, flocks are the clumps of particulate matter that we're creating here. We want to create flock. We want to create that snowflake. Super important. Alkalinity, like we talked about, super important. It's the measure of the capacity of water to neutralize an acid. So it's loosely related to the hardness. It's the calcium carbonate saturation. It's that, capacity. The inorganic coagulant, the cationic coagulant in this case, it reacts with that alkalinity. We saw that, right? Those OHs in the water on those 6 arms, and once all 6 arms are full of alkalinity, that thing's ready to go. This is called hydrolyzed. So once a coagulant is hydrolyzed, that means that the alkalinity from the water, it's ready to go. It's a strong bond and it will start working for you. It's perfect. But it needs that alkalinity, right? It's like that sports car. You got to put gas in it. No gas, you ain't going nowhere. Same idea. Hydrolyzed is that word. So now that it's hydrolyzed, the metal salt's broken down, and the metal, in this case aluminum, binds with those hydroxyls, also called alkalinity. Then we're ready to go. Alkalinity is required to complete the coagulation reaction. I can't stress that enough. There's no alkalinity in the water, no flock can form. And you can put as much coagulant as you want in the water. If you run out of alkalinity, it isn't going to work. So like I said, what happens is that operators, and especially new operators, they'll put this coagulant in. It's not working. I guess I should add more. they add more. Instead, what you get is foaming, and you get a sludge that's raising to the top, and it's not working right, or the color's not being removed. So you go, well, the product must be wrong. You switch products, try something else, and really all along, it's alkalinity. And you might have to add alkalinity in the form of some sort of caustic that will have to be added in order to make this work. A lot of creek sources are sources that have water that haven't been in contact with the environment very long, tend to have very low alkalinity. And that's the problem. Because of the low alkalinity in the water, it tends to absorb a lot more color and create a lot more colloids. So it's kind of a double-edged sword, that the water that needs the alkalinity or the coagulant the most is usually the water that has the least amount of alkalinity. So it's always very important to make sure you have enough alkalinity. The coagulant must react with the alkalinity and in the process form these flocks. Alkalinity is the limiting factor, and we talked about that, no gas in the car. Let's talk a little bit about the chemistry. You're not responsible for that, but let's look at it from a chemistry standpoint of what happens in that water when a coagulant's added. It does a reaction. This is aluminum sulfate over here. And when we add it to water, it also is looking at the calcium carbonate in the water. So all these three things have to happen. There we go. For a good guide, this is probably a really important thing. Let me make it blue over here. There we go. Every 1 milligram per liter of alum added to water requires 0.45 milligrams of alkalinity. And alkalinity is measured as CaCO3, which is calcium carbonate. So that's really important to understand, that if I'm going to add 1 milligram per liter of alum, then I better have 0.45 milligrams per liter of alkalinity. So when you do your alkalinity test, that's something to think about. If I have to add 20 milligrams per liter of alum, I better make sure I have at least half of that in alkalinity. So I should have at least 10. And remember, it could fluctuate, so you want to have some extra in case. Okay, we talked about the arms. So here's the thing. This is aluminum sulfate right here. And you can see when I take it out of the package, this is aluminum sulfate. Now, when I actually do the reaction, what I'm going to do is I'm going to put this in, and I'm going to take these OHs. So I'm going to basically, these just disappear into the water just like that. And OHs, let's put those in. Those OHs are going to go here. So that's an OH. So I'm going to need 6 of them. And these OHs come from the water. And they're going to go in and they're going to bond onto here. Now, this is alum. So you can imagine I need a lot of alkalinity to make this work. But I'll show you something really interesting. I'm going to put 3 of these guys back here. Hang on. Right on. There's 3. So now, if I look at a different product, and let's talk about polyaluminum chloride, and that's a different product than alum. And what it does for us is that, and I'll draw those in. There's my drawer here. Here we go. When I get it, it looks like this now, right out of the package. It has 50% alkalinity built in already. So when I take this out of the package, I'm going to put it in the water, it already has these OHs. So it's 50% pre-built in, which is great. Now I only need 3 more to make this work. Before I needed 6. So it actually, I can now put this into water with less alkalinity and it's going to work. So that's great. Of course, the product is probably more expensive, but I don't have to adjust any chemistry. It's going to work in my favor. And that is called polyaluminum chloride, or PAC as it's called. And it's built-in alkalinity, which is great. Now, there's one to be used a fair bit now. And this one's called ACH, or aluminum chlorohydrate. And I apologize for my horrible penmanship, but it's really hard to draw with a mouse. Some of the new products out there actually are like come out of the package like this now, which means it's almost 80% built-in alkalinity. And that's awesome. Now I don't have to use, 2 things are good about this. See this SO4 here? Only one of those are going into the water, which means I'm putting less sulfates or chlorides into the water product. That's good, because you don't want a lot of sulfides or chlorides in your water. The other thing that's good here is I only need 1 OH taken from the water to make this work. That's even better. I can have super low alkalinity. I don't have to add any extra chemical, and this thing's all built in for me. Unfortunately, it's a lot to make this work, but the reaction is so much better, so much more efficient, and you use way less product. You'll use probably 50% less product or coagulant, which means you can have smaller pumps, smaller tanks. You know, it just works a little bit better. But again, there's a trade-off with cost because the product itself does cost more. All right. Coagulation and flocculation effectiveness, and again, it's the type and concentration of your turbidity, suspended matter, or colloids. Type of color you have there, how deep is that color? Yellow? Is it like orange? Is it really brown looking? How much alkalinity do you have in there? What's your pH? We know it's going to be 5 to 7 is ideal. And temperature. We know between 2 and 20 it's going to work well, but outside of that, it might not work as well. We're also going to look at the type of dosage and type of coagulant or coagulant aid. And we're going to talk about coagulant aids a little later in the lecture today. We're also going to look at the degree of coagulant dispersion, which means how well was it mixed, that rapid mixed, and how much mixing energy do we have during the flocculation. And we'll talk about flocculation here in a second. Just a reminder about pH. Now, pH is a measure that describes how much acid or alkaline or basic the solution is, measured on a scale of 0 to 14, where 7 is the neutral. We should look here that some typical things that we deal with in the water treatment industry, stuff like CO2 is down here. Or sorry, up here in the acid range. CO2, any acids we use, it's all going to be sitting up here. Whereas down here, a lot of the product you're going to be using, especially coagulant, is going to be sitting down here. And it's going to be a bit on the basic. But pH for us, to make sure that everything's going to work well, should be 5 to 7. So we need to be in this range here for coagulation to make sure it works well or works the best. Again, the range, and that's changing more and more, is 6.5 to 8.5, and that is usually most treatment processes work best. We learned again in disinfection that coagulant and chlorine starts to not work as well once we get over that 8 pH. You know, everything kind of works well in that, just before 8, and it doesn't work well or when you start getting or more acidy or into the 5s. So that's that range I really like to try to stay in as much as possible. How do we find how our dosing is going to work? Like, how do we get our chemicals in there? And we're going to do something called a jar test. We're going to look at all these different things. We're going to take water from your process. We're going to put them into some mixing jars. We're going to look at the pH and all these things, and we're going to do these tests. We're going to add chemicals in small to these jar testers. And this is an older jar tester here. So inside these beakers and these square beakers, they're going to replicate your process. So you're going to put the water in, and you've got to do this right away because you don't want to put the water there the night before because it's not going to be the same temperature as the water in your plant. So you want exactly to replicate the water in your plant. So you put your water in here, you're going to estimate the chemical and try different chemistry and different types of chemicals to see how you create the flock, which is great. We'll talk a little bit about dosing equipment and the dosing equipment that is used to introduce these coagulants to the water. Sometimes there's a dry feeder, and you can get the product in a dry form, and you'll have to add water to it. And adding water to a dry product is called slaking, and that's done less and less now. We see this now more in liquid form. And so you're going to use some sort of liquid feeder to and pump to something similar to this here, either a diaphragm pump or a peristaltic type pump that will pump the product or the liquid to the water. The objective of all this, right, is the coagulation and flocculation, which we'll talk about develop this flock and to make and not just develop it, but also make it do the work for us. So coagulation is making this flock. Flocculations now is making this flock work for you. We want to get rid of all these things, right? The colloids, the turbidity, color, the algae, all these things in the water. And we want to get it ready to remove out of the water. That's exactly what we're going to be doing here. So coagulation is making these flocks. Flocculation now, what we'll talk about, is making these flocks work for you. They make them get these other products out of the water. So before we go to flocculation, I'm just going to pause right there. I'm going to show you a quick video if I can get it up here, and then we'll have a quick break. So bear with me here, and I will get this in a second. I'm hoping it will work, but we'll try it anyway. Just bear with me here while I bring this video up. I took a couple of videos of some really important things that would be very important to see. There we go. All right. Okay, I'm going to try to share the screen with you guys again here. Let me know that you can see that. Give me a thumbs up. There should be a grate there and a picture that comes up. And if you can see that, give me a thumbs up, please. Awesome. Great. And we'll try this. This is actually at my plant. So let me kind of explain what we did here. We added a coagulant to the, and that coagulant went through a rapid mix. And I can show you that too. We got a couple of videos here, a couple of minutes, which is perfect. We created a flock, right? So we, bang, it mixed really hard. We put it through a flock mixer, and I'm gonna show you those as well. If this video works, I could show you a couple other. And then we created a flock. And the flock honestly should look like snow. It looks like it's snowing. And that's all these little particles of coagulation. So let's take a look here. I'm going to show you 3 videos. The first one's going to be this one. Then we're going to look at my rapid mix and into my flocculation, which we'll talk about after the. So here's the first video. I just have to make sure that you guys can hear it as well. Share sound. And okay, here it goes. Okay, so you can see with this nice light here, you can see how those flocks look like. It looks like snow, right? Have you ever driven with your headlights and you can see the snow, and that's exactly what we want. The next step in the process is a dissolved air flotation. And of course, we're going to use air. I have an empty basin here. We'll take a good look at it. You can see those nozzles down there? So water's going to come up over those nozzles. Those nozzles there are going to bring air up. It's going to push the product, and the good water stays at the bottom. It gets collected with those white pipes that you see at the bottom here. Behind me is an actual working DAF. You can see it here. Here we go. You can see the whiteness of the water, right, as that air bubbles, and all the product. You can see this dirt starting to come to the surface here. And again, as it's moving through, it collects more and more dirt. Okay, so that's the first one. So we're going to talk about dissolved air flotation in our lecture a little bit after the break. You can see that those flocks, that's what I'm collecting here. And all that brown stuff that you see there is those flocks. So let me just other little videos here. Let me get those ready to go, because I think these are really neat for you guys to see. Okay, let's. It just takes a bit for the video to come online here. Okay, perfect. Let me get rid of this one. Okay, I'm going to share my screen again. And let's go full screen here. Okay, let me know if you can see that. You should see a set of stairs with a yellow bar at the top. Give me a thumbs up if you can see that. Perfect. Okay, so what you're going to see here, and unfortunately I should have showed this video first. So at the top of these stairs, we're going to look at a rapid mix chamber, right? And ours are fairly big. Keep in mind today when I did this video, we're probably producing in the neighborhood of 15 to 20 million liters a day. And that was the flow coming through the plant when I did this video. What you're going to see here is a rapid mix tank. So chemicals are added just before this tank or into this tank. There's some mixers. You'll see 2 brown or blue mixers. They are mixing. That's your rapid or flash mix. Then we're going to go and take a look at a flocculation chamber, which we're going to talk about after the break here. Now, this is a great video because I have one side of my plant offline right now. So you can actually see a tank that's in operation and a tank that's not in operation. And so it gives you the size of the impeller. So let's take a quick look at that. That's the chemical alley part. So what we're going to do now is we're going to go up into the main plant floor. First thing we're going to see when we come up here, fairly large filter floor area. And we're going to look at our flash mixer and then into our flocculation tanks. So under these grates here, this is that blend box we saw below. Water in here is moving, mixing, and you can see the motors here. And they're providing that mixing, that flash mixing. Now, what's water and chemicals mixed here that's going to go to the flocculation tank? Here's one of our flocculation tanks here. You can see this water here right now, it's 70% lake and 30% creek. And it's mixing here with a fairly large mixer. I have 3 basins. Mixing energy decreases as we go along. Now today we just happen to have our other train down so we could actually take a look at what those mixers look like. Here's an empty tank here. And you can see how deep those tanks are and the mixers that are in them. Gives you a pretty good idea. So that for us, we have water from a number of different sources. So I take water from the creek and I take water from a lake and I blend it and I put the right amount of coagulant in, flash mix it, and I put it through those flocculation. And you can see those big propellers that are in the tank. And said there was really important is that each tank, as it's moving to the next tank, the water, the mixers are much slower. Every tank, slower and slower. And then it comes around the corner and it goes to where that light was, where all those flocks were. And again, it looks like, it's hard for you guys because you don't have a lot of snow, but it looks like that. It looks like a bunch of snowflakes suspended in there. And that's exactly what it is. Okay, let me move things around. Awesome. Okay, so it is, looks like 9:08 your time. So let's take a 5-minute break. Ignatius, we're going to take a 5-minute break, and then we'll come back and we'll get into flocculation. 5 minutes.